And a good morning to good morning, everybody, and a very hearty welcome to all of you for this meeting. So this is the meeting that we have been planning for a long time, recognizing the importance of teaching physics in an engineering curriculum. And it is somewhat providential that we had only yesterday the Dayanand Sagar University Foundation talk, which was given by Sri Narayan Murthy, who is well known to all of us. And in fact, Narayan Murthy mentioned in his talk that we use a lot of technology, but most of the technology that we use is invented outside India. And that sort of underscores the importance of physics education in engineering curriculum. As a matter of fact, Sri Narayan Murthy mentioned the contributions of a large number of important scientists, educationalists, and about 80% of the names that he brought up were all physicists, and not just Einstein and Niels Bohr, but also John Bell. So I think it is providential that we have this meeting this morning. May I request our Dean for the School of Engineering at Dayanand Sagar University, Dr. A. Srinivas, to please make his opening remarks. Srinivas?
Thank you, sir. Deshmukh, sir. Thank you so much. Very good morning to this very unique and highly focused colloquium on significance of physics education in engineering curriculum under NEP. I am Srinivas here. I am the Dean School of Engineering at Dayanand Sagar University. I consider it a great honor and privilege to be a part of the deliberations on this current and much needed topic. The colloquium is more significant in view of the NEP 2020. NEP 2020 lays particular emphasis on the creative potential of each individual. Education must develop not only cognitive capabilities but also social, ethical, and emotional capabilities and dispositions. Physics plays a very important role in the engineering sense. A great part of the technology can be considered as a last insight of physics. The well-known fact is that the current state of physics research in any country determines the level of its technology. Physics is the philosophy of nature. The deliberations of today will be formally presented to Dayanand Sagar University authorities, and reforms will be applied to enhance the content of the science in general and physics in particular in the engineering programs. Attempts will also be made to present a report on today's colloquium to the government departments to contribute to the implementation of NEP 2020. We have with us very highly distinguished guests who are authorities in their own domains. But for the efforts of Professor Deshmukh, it is next to impossible to have this distinguished panel to be available in this forum to present their views on this current and most needed topic. I take this opportunity to welcome Dr. P B Sunilkumar, Director IIT Palakkad, Dr. Bhanu Prakash, Director TCG Sequire, Sri Kumar, Satish Dhawan, Professor ISRO, Dr. Shekhar C. Monday, DG CSIR and Secretary DSIR. I would like to remind our colleagues who are all attending here that this panel is amazing. I am getting more excited to be a part of this discussion. I welcome the Chancellor, Pro Chancellor, Vice Chancellor, Pro Vice Chancellor, and the Registrar for this event. And some of them could not be here for some pressing preoccupations. I also take pleasure in welcoming the deans, chairpersons, faculty colleagues, and students of DSU, and also other guests from within and outside of Karnataka. I now hand over to Professor Deshmukh to continue with today's deliberations. Thank you so much.
Thank you, Srinivas. Thank you very much. As Srinivas mentioned, we do have a very distinguished panel of speakers today. And there is a good reason for it. We realized that the Swachh Bharat Abhiyan became an important tool in India, and it became an important movement in India when the Prime Minister himself took the broom in his hands. And we felt that to bring about revolutionary changes in physics education, in engineering curriculum, because we do seem to have a problem that, in the engineering curriculum, we have only one course given to students who come straight out of high school. And that course, it's a one semester course. It has got everything from the Schrödinger equation to the nano sciences, nanotechnology, lasers, whatnot. And everything is delivered in one semester. And, that really tells us that there is much that is desired in changing the curriculum at the basic level. And these changes cannot be brought about unless people at the top, and that is the reason this very distinguished panel, each one of them has contributed tremendously to research and advances in basic and applied sciences. We have Dr. Sunilkumar, we have Dr. Bhanu Das, Dr. Kumar, Dr. Sheikh. They have made important contributions to research. They continue to make important contributions to research and push the frontiers of science and technology. And we felt that people at their level must get involved in this issue. And that is the reason we have requested them. We are very grateful to all of you, gentlemen. Dr. Sunilkumar, Dr. Bhanu Das, Dr. Kumar, Dr. Shekhar Mande, all of you to have given your very precious time. You're very busy. And in fact, we made a slight change in the schedule this morning. Dr. Sunil Kumar's talk would have been the first one, but then Dr. Shekhar Mande has an appointment with the Lieutenant Governor in Ladakh in a short while from now. So we have advanced his talk to be the very first one. So I will not come between you and his talk. May I request Dr. Vijay Kumar to please introduce Dr. Shekhar Mande. Vijay?
Yes, sir. So good morning to all, and thanks to all the respected dignitaries and participants. So I'm very happy to introduce our renowned scientist, the Shekhar C. Mande. The Shekhar C. Mande is born on 5th April 1962 in Pune, Maharashtra. He is an Indian structural and computational biologist. He did his MSc in physics from University of Nagpur. He holds a Doctor of Philosophy in molecular biophysics from the Indian Institute of Science, Bangalore. Following his PhD, he joined Professor Wim G.J. Hole as a postdoctoral fellow at Discus University, Groningen in the Netherlands. Since 2001, he was a senior scientist at Center for DNA, Fingerprinting and Diagnostics, Hyderabad. Between September 2011 and September 2008, he served as director at National Center for Cell Science in Pune. Currently, he serves as Director General of Council of Scientific and Industrial Research, that is CSIR, come Secretary, Department of Scientific and Industrial Research, Government of India. He was awarded in 2005 the Shanti Swarup Bhatnagar Prize for Science and Technology, the highest science award in India in the biological science category. So the Shekhar C. Mande research thrust areas are structural biology and X-ray crystallography, structural characterization of Colloquium, tuberculous proteins, and also the computational analysis of genome, wide protein interactions. The Shekhar C. Mande, the role in national international advisory bodies. Dr. Mande is a current Director General of CSR and Secretary of the Department of Scientific and Industrial Research, that is DSIR, Ministry of Science and Technology. Prior to this, he was the Director of NCCS Pune, an autonomous institute funded by Department of Biotechnology, Ministry of Science and Technology, Government of India. He served on many advisory committees before moving to Delhi in 2000, including task forces of Department of Biotechnology and Department of Science and Technology, Government of India. He used to chair the Basic Science Task Force of the Department of Biotechnology and was a core member of biophysics, biochemistry, molecular biology, and microbiology task force of Science and Engineering Research Board of the Department of Science and Technology. He also served as member of the Management Council of Tata Institute of Fundamental Research (TIFR) Mumbai as a representative of Maharashtra state government. He is to be a member of Management Council of Solapur University and Savitribai Phule Pune University. He is a member of governing body of Indo-French Center for Promotion of Advanced Research and served as member of Research Council of the Institute of Genomics and Integrative Biology, New Delhi. The prizes and awards of Dr. C. Monday. He got the BM Birla Young Scientist Award in 1999 and Wellcome Trust International Senior Fellow in 2003 to 2008. And also he got a prestigious award, that is Shanti Swarup Bhatnagar Prize for Science and Technology in 2005. And also he is a fellow of Indian National Science Academy, New Delhi, and also fellow of National Academy of Sciences, Allahabad, India, and fellow Indian Academy of Sciences, Bangalore, and also is a BC Goha Memorial Lecturer of Indian National Science Academy in 2017. BK Bachawat Memorial Lecturer of National Academy of Sciences in India
Vijay,
2017. So
Vijay,
thank you all. So this is over.
There is no way we can
Yes, yes, sir.
introduce somebody like Shekhar who has such
Yes,
rich contributions.
yes, sir. Yeah, I'm very happy to read
So
this brief biography. This is also brief one.
yes, it is. It certainly is a fraction of what we can say about Shekhar. So thank you very much, Vijay,
Thank you.
and welcome, Shekhar. So please address the gathering.
Thank you, sir.
Thank you so much, Professor Deshmukh. Thank you so much for this invitation to speak along with so many distinguished guests at the Dayanand Sagar University organized event. My internet connection is somewhat weak, so you may find that voice is breaking or the video is breaking. I am right now in Leh, Ladakh, but I will be as brief as possible. I realize that I have taken away the time of Professor Sunilkumar, so I assure you that I will not take too much time. So we are discussing NEP 2020, but related to NEP 2020, we also discuss about the contributions of Indians to the world of science in general. Professor Deshmukh mentioned about Mr. Narayan Murthy talking about general physics and general scientists and all. What I would like to say is that the contributions of Indian scientists have not been very minor, as many of us like to believe, many people would like to believe. In fact, Indians have always made for centuries, and especially in the last 100, 200 years, great contributions to the world of knowledge. You know, I mean, the whole lot of names come to the fore when we talk. So we'll not take names, but nonetheless, great many discoveries have been made. And in biophysics, we are very proud to say that many of the Nobel laureates of physiology and medicine, or many of the Nobel laureates of chemistry, we may not be able to name them or their contributions, but one person who stands out, despite not getting Nobel Prize, whose name will always be remembered in the terms of biology, biochemistry, biophysics, is G.N. Ramchandran. So this we are very proud, and that all his work was done in Madras University, whatever he contributed. Significant contributions to the world of knowledge, although they may not have been recognized by awards or fellowships or whatever. Now, this has been very apparent in the COVID period. In the COVID period, starting from the understanding of the biology of the virus, why some people are getting more affected than the others, and why is the Delta such a difficult strain that has emerged. All this, the basic fundamental work, a lot of it happened in India and has been published in some of the most frontline visible journals and is being cited now extremely well, including the multiple papers in Nature, Science, PNAs, and so on and so forth. And that's been actually a very, very good development that we see. We literally see coming of age of Indian science. But what is also important is that the science, when it is translated for the benefit of larger benefit of society, the translational aspect of that science also seems to have come of age in this period. Although many of the translation aspects are not rocket science, for example, generation of oxygen, what we see through the PSA technique or the PVSA technique is not rocket science. It has been known, but it had to be translated and made available. And only yesterday, we crossed something like 1,000 plants across the country for medical oxygen generation. So what COVID period has allowed us, the entire S&T community in the country, is have that firm self-belief in ourselves that we can contribute to the frontiers of knowledge. At the same time, we can also translate this knowledge for the societal benefit. And in fact, some of the translational work has been so fundamental that at least in one of the cases I remember, we were in direct competition with two groups, one in MIT and one in UC Berkeley. And that was the use of CRISPR-Cas technique in the diagnosis of COVID-19. And one of the Indian institutes did compete with MIT and UC Berkeley. And simultaneously, as the two other institutes were bringing this kit to the market, we also did that in India. So we should be extremely proud of what we have done. Vaccines, of course, as Professor Deshmukh also mentioned, there has been some wave of thinking in recent times that we have to make lives of our common people easier, right? I mean, in multiple ways, we have to reduce bureaucracy in much of the things, and we have to see how common people benefit by the advancement of knowledge and science and technology and so on and so forth. And at this moment, we are in the process of writing a document called Ease of Doing Science. But the government has also announced the new science and technology and innovation policy some months ago. But the most significant aspect of it is the NEP 2020. All of you would agree with me, those of you who have read NEP 2020, fundamental transformative. If NEP 2020 is implemented in its true spirit, I think Indian education system would be transformed as per se. It deals with multiple different aspects, starting from primary education, higher education, vocational education, and so on and so forth. And what it tries to do, at least at a primary education level, it emphasizes the fact that a lot of learning has to happen by experience, what we can actually do with our own hands and experience. I don't think anyone can deny that that is probably the best form of learning, what you actually do yourself. But also, learning in our own mother tongues. There are so many different languages in the country, and if we start imposing either Hindi or English on everyone that you have to learn in that particular language, you would have alienated a large population which lives in not so well endowed conditions in the country. I mean, if you remove the cities in the country and go to rural areas, the penetration of English and Hindi might be there, but nonetheless, the understanding of whatever is being taught in the classes is best in the mother tongue. And that also is emphasized in NEP 2050. When we come to higher education emphasizes the fact that it has to be integrated. The education has to be integrated. And that's precisely the point that Professor Deshmukh mentioned, that having introduced only one semester course on physics to engineering students probably is not going to serve us good in the long term. We must have combination of all the subjects throughout the entire curriculum. Even in the engineering sciences or medical sciences, we must have integration of many different aspects of knowledge. So physics is just one part of it. And indeed, the physics plays such an important dominant role in all our technology developments and all, that if we don't train students in physics, I think we will not have the desired effect 20 years from now. The students who are being churned out now, who would be making contributions for future of India and future of society in general, if they are not given proper holistic picture, I don't think we would have done our job well. And that's precisely what NEP 2020 also dwells upon in fair amount of details on how we can actually give holistic education to all our children. And if we are able to do that in the true letter and spirit, I think we would have transformed Indian society for future. I do hope that we all take it in that particular spirit. And I do hope that we all, I see here directors of IITs and other places here, that we can actually start implementing in that correct spirit as is actually explained in the NEP 2020. Thank you all very much for inviting me here. And I look forward to some of the discussions with Professor Deshmukh later. Thank you.
Thank you very much, Sheikh. It's a visionary remarks that you have made, and I think it's a great opportunity for Dayanand Sagar University to mull over your ideas, grasp them, think through each point, and then bring about sufficient reforms so that we can make a significant contribution to the changes which are necessary under the NEP in our engineering curriculum. So thank you very much. We will now go over for the next talk, which will be by Dr. P B Sunilkumar, who is a distinguished physicist. His contributions to soft condensed matter physics, computational biology, and so on is very well known. Let me invite Dr. Radhika to please introduce Dr. Sunilkumar. Radhika?
Sure, sir. Good morning, everyone. It's an honor for me to introduce to you Professor P B Sunilkumar, who is the director of IIT Palakkad and is a renowned physicist known for his research on soft matter and biological physics. He is also a professor at the Department of Physics at IIT Madras. He completed his MSc in physics from Calicut University in 1987 and PhD from RRI in 1994. He then worked as a postdoc fellow in Raman Research Institute, the Institute of Mathematical Sciences, and Max Planck Institute for KG Gome till 1999. He joined IIT Madras as an assistant professor of Department of Physics in 1999 and has been a professor in the department from 2006 till being appointed as director for IIT Palakkad in January 2017. He is also a fellow of the Indian Academy of Sciences. He was recently selected for Professor M.B. Piley Award for the Distinguished Academician of India in 2019 by CUSAT. His current research interests include fields of active systems, polyelectrolytes, membranes, and rheological properties of micellar solutions. I now request Professor Sunil to deliver his talk.
Thank you, Radhika. Sunil?
Thank you, Professor Deshmukh. And thank you to the Dayanand Sagar University colleagues and other distinguished speakers here. It's a great pleasure to actually deliver this or whatever I can say on this topic, because I know this has been a very favorite topic also for Professor Deshmukh, and for quite some time. I know him for a long time in the Department of Physics at IIT Madras. And many times this topic has come up even in IIT Madras, and so it's a pleasure definitely to discuss this and present some of my views. So just to make the my presentation a little bit more focused, I have a few slides which I will try to share. I hope I can share right. So could you please enable screen sharing for me?
Imtiaz, can you take care of this? Imtiaz, can you arrange that Dr. Sunilkumar can share his screen?
Right now, I'm not able to share the screen, but
So do you have the option of share screen at the bottom?
yes, but it says host disabled participant screen sharing. So I think you'll have to do that.
Oh, I think Vaishali is
Okay, so in the meantime, let me just get started on this. So, because we also at IIT Palakkad also, we are going through a revision of curriculum. We have finished here 5 years, 3 batches have come out, and I think that's 7th year we are now. So we have 3 batches have come out, and with BTech degree. So we decided to go through a curriculum and regulations change in the institute, and we had very extensive discussion on this. So some of these discussions are fresh in my mind. So I know what the difficulties are in coming up with the BTech curriculum and in today. Okay. So so that is what. Okay, so I'll just share my screen. Just give me a minute.
Yeah, I think he has enabled it now.
Yeah.
Can you sir please check?
Sure. I think I'm seeing that.
Yes, it is up.
Yeah, let me just go through. So I hope you're able to see my screen, right?
Yes. Yes.
So so what I was saying is that we just went through it, and we have just approved in our Senate the new curriculum, which starts in 2023 academic year, 22-23 academic year. So we have some of those discussions and difficulties which are quite fresh in my mind. So I hope I will be able to convey some of that to you. So as we know that science is the mother of all engineering. So we have no question about that. So I don't think we are even discussing today the importance of physics or mathematics or any other science topics in engineering curriculum. It is extremely important. So what we are talking basically about the importance of teaching those things, right? So to the students. So engineering is built on science. So there is no dispute about that. So now, so we look at how we can, on how much science we should teach, or how much we can teach for engineering curriculum. That is, I guess, is the main topic of today's discussion, right? And as I said, here I just quote from a recent article. Like physics is taught badly because even teachers struggle with basic concepts. So now this is a loop, okay, which we get into. So teachers struggle with basic concepts, so it is taught badly, and the students don't feel why they are taking this course, okay, and then it kind of propagates. So this is and many engineering teachers which we get today have gone through this kind of education too, okay. So they also don't see why this has to be taught as a physics course, or in fact, they even had some discussion on how much mathematics should be taught. And I'm surprised to see that some students who come in today, even to IITs, and to areas like computer science, ask me that, we came to study computer science, why are we being taught mathematics? Okay, so this looks like a mathematics course. It's not a computer science course. So it's that is an understanding students have, and that is this understanding some of the, unfortunately, our society is propagating too. So there is definitely a need to have a change on that. So that is indisputable that the importance of physics in the curriculum and engineering curriculum, and the question is how we can deliver that, right? Okay, so importance to say that there are two ways. One is, of course, the concepts, as I said, has already been stressed by both Sheikh and Deshmukh both, that concepts are important if you want to go to our Atmanirbhar Bharat and things like that. All these inventions. So concepts should be strong enough to should be strong in the student's mind, right? So that they can actually come up with new inventions and new ideas and new things, etc. Okay. And the tools we learn and the tools we have actually shape our thoughts, right? We all know that. If you're very the way we think about anything, any solution to any problem which we see, or anything which we need to innovate on, that the way we think about solving problems, or the way we think about innovation is based on what tools we know, what tools we have, like both in thought and in our hands. Okay. So in that sense, it is extremely important that the students have very thorough basics on the physics concepts and mathematical concepts, when they take up engineering. And in today's world, of course, biology and chemistry also has become as important because there's a strong emphasis on medical and biological engineering, right? So, so that is all the science concepts become now extremely important for today's engineering education. And another problem is with the whole process of changing this, which I find is that it's very difficult to convince people on any of these requirements, because the results of what we do today and what kind of curriculum we put up will be evident only at least 10 years down the line, when we have these people who take up these UG courses today come back into their productive life of academically, right? So when they come back to academics, or when they go into companies or whatever, okay, when they have to contribute actually, so that's the point where this will get reflected. But it'll be 10 years at least we have to wait. So it is kind of difficult to convince people that by the 10 years it becomes too late to see that. So what we can only do is look at what we have today and what people are coming into the institute and into the academic world, and also have connect with industries. And then there are people in those spheres, and both people who are now coming to the academics and also people who are in the industries who understand what they lacked in their UG education, and hence they'll be actually willing to support this kind of an idea of having a more thorough basic course in that way. So, for example, if I'm just giving you a few examples here, that is that main point which I wanted to say, I've already said, but just to give you a few examples here, when we talked about physics basic thing, okay, the education in physics, okay, we said, okay, students should know how to use vector calculus, right? And vector calculus and mechanics are connected. Okay? So how do you do mechanics and using vector calculus, which is something they have not learned. They have heard about this, but they have not learned in properly. And there is what a better way to do actually vector calculus than actually do this in mechanics. Right? And similarly, they have talked about, they have learned about mechanics of individual bodies. Okay, but they have never exposed. They have never been exposed to, and they have never been taught anything called vector fields. Okay, so instead of directly putting them into going to antenna design and electrical engineering applications, they should go through a proper EM theory, okay, where they actually understand what a vector field is, okay, and then also understand the vector fields through continuum mechanics. So they use it a lot later. They will talk about stress, strain, everything later, okay, but they would not have really understood the concepts of and the tools of vector fields and in continuum mechanics. And similarly, now many chemical engineers, many bioengineering people will be actually talking about flow of particles, counting particles. They talk about the concepts of viscosity, the kind of all kinds of things. Okay? But they would not have exposure to many particle physics, right? So so concepts of statistical mechanics. Okay, so extremely important. Okay, and it used to be taught and should be exposed. Of course, when I say this, I'm talking about different parts of engineering. I will come to that in a minute. And then, of course, today's engineering is all about micro nano world, and we again, Professor Deshmukh mentioned that already. So there is a lot of concepts there which you need to pick up. Okay, the whole world of quantum mechanics, right? The micro nano and low temperature things which people do a lot. The whole world of quantum mechanics is there, which has to be taught. It has to be understood if they want to do anything, any meaningful, not only meaningful contribution, to actually get a feel for the whole subject. So so we can go on this and then many things, and just again, let's say that if you now think about that's a basic concept. Now, even if you think about in level of just physics for the application minded, somebody is not interested in looking at the foundational theory and things like that, it's okay. But even there is physics for the application minded. So one way, we had a long debate on this here. Okay, we said we are not trying to make all students who come into engineering into a physicist, okay, or a scientist. Okay, we want them to be engineers, but we want them to be good engineers. We want them to be good engineers. They understand and they can contribute into engineering. Okay, not just become technicians. So so one way we thought about is to teach physics along with engineering topics. Okay, don't separate them out. Okay? Teach them together. Right? So you can, for example, as I said, like if you take an electrical engineering, you take a antenna design or something they're teaching, they have to teach. They have to have a part of that which will be on EM theory. Again, that could be taught by a physicist himself, right? A physics teacher, not taught by an engineer. Physics teacher teaching that concepts clearly, so that they also make a connection with the application. And so basically, it's saying that scientists co-teach courses with engineers. Okay, that is the concept which we are trying to implement here. Okay, and so that people make that connection very quickly, and they don't feel that why I'm learning this. Okay, so this concept. And then instead of now, there is a problem here that we have 4 years, right? So the practical problem, we have 4 year students coming, and they take approximately 48 courses. If you took at today's engineering curriculum in all IITs, it's about that. Okay, about 140 something credits. Okay, 141 to 145. Okay, is the basic BTech curriculum, I think. Okay, and places where they offer honors like we do. Okay, they take another 15 credits. So that means another 5 courses, 4 to 5 courses. Okay, they do. Okay, that is what they're doing. Okay, so now within this 48 courses, we want to make an electrical engineer or a mechanical engineer or a civil engineer, right? And so the departments feel that if they're going to have a civil engineer or a mechanical engineer, they should have a basic core of that subject, which I'm not denying. Okay, of course, we are going to call somebody a civil engineering, that person better know what civil engineering is. So they have to take some courses in that. So now, how many courses can you pack, right? And remember, I think a few years back, okay, maybe not few years, maybe a decade back or more, we had 165 credits. Okay, actually, a few years back, we had 165 credits. Maybe a decade back, we had 170 something credits. Okay, for the four-year BTech program itself. Yeah, but that has come down a lot because there's a lot of pressure on the institute to say that students should have more freedom, they should have more time to think, they should have more time to work at home and do things with hand, they should have innovation centers, and they have to spend so many other things. Okay, so you cannot have so many courses. So now we come down to this. Now the question is, what is the solution, right? So I'm definitely not one person who would recommend at any stage what is called a one-course engineering physics. Okay, and that is a disaster. Okay, and I completely agree with Professor Deshmukh that something called an engineering physics, which goes from which covers everything, is no use at all. That kind of exposure they must have had in the school already. Okay, because they have been again exposed to a lot of things in the school without going through any detail. And so that is not useful. So what we should do is, my feeling is that if we have reduced to one course in the first year, okay, and one course as part of the core, and the core basic things they do, okay, yes, that be one subject, okay, which is common for all engineering, one subject, not a mixture of subjects. It could be one, it could be if everybody feels that they should be taught quantum mechanics, or they should be taught mechanics, classical mechanics, yes, let's teach one of that. Okay? And then you have more electives, and electives are also basic courses. And you say, so what we have done here in IIT Palakkad is to say that, okay, they have, as science core, 2 courses, okay. Science core, there could be chemistry and physics, right? So there will be science core 2 courses. And then they have to take compulsorily 3 more courses in science, okay, before they finish their BTech. So the total credit requirement for science we have fixed as 15, which means about 5 courses. And we say, okay, 2 courses they can take. Any 3 courses they can take from any science, I think, from under science category. Okay. They have to do electives, but that they can choose. They want to do EM, electromagnetic theory, or they want to do statistical mechanics, so they want to look at more courses in quantum mechanics. So they can do that depending upon what branch they are in. Okay, and so this is the way we have proposed, just to take care of this constraint of 48 courses, and at the same time having to have and insist that they should learn some some basic science, okay, correctly, okay, and similarly for mathematics, etc. So that is one solution which we have proposed or we have put in here, and we have to see how that will work out. Right. And so again, just to drive home the points, I have asked during those discussions my colleagues here, come up with why they would want to learn physics. Okay, so of course, these are what are some of the examples I'm showing is obvious to everybody today, right? Transistors that come to 5 nanometers, and the gate length is now 5 nanometers. We're talking about a few lattice points. So now we are actually solving, when you're designing circuits, we are actually solving Schrodinger equation. Okay, so people need to get, and there are packages, of course, which do that. But something else, we become a package user, and we want to become a package writer. We need to understand all of this stuff. Okay, so that is another issue. Okay, so so let's come to microelectronics, and if you look at mechanics and engineering, right? So there are design principles, okay, and even materials design. Okay, we use a lot of principles from physics, right? So that is so whether building a bridge or understanding the stability of an old structure, okay, which are we're talking about here pictures I'm showing 1,000 years separated, and then we need to understand all of this. Okay, so then we need to have completely understand the materials used and the stresses and the strains which these things they will handle. So force, stress, strain concepts, etc., are extremely important for a lot of fields, like how much force we can apply, okay, into a wheel, okay, how much how much pressure a tire can withstand, and how much, what kind of patterns, the tread pattern should be there to get maximum friction of the ground, variety of topics, right? And when it comes to electrical engineering, there is, now we talk about band pass and band stop filter designs, and again, filter design, okay, that we're talking about. Okay, again, you are talking about small scissors structures being made. Okay, and again, we need to understand a lot of electromagnetics in this for the such designs. Okay. And so I can go on this, like if you take again mechanical engineering, you can talk about mechanics, we can talk about materials, like kinetic theory, thermodynamics, vector fields, gradients, so many things. Okay, now if you come to even bioengineering, right? When we're talking about a laser surgery, okay, we need to understand how the heat is dissipated, how the light is focused. Okay, and that goes from a surgery of an eye to designing the a solar energy collector, right? So there is whole whole spectrum of engineering which we need to do to where basic physics and understanding basic physics is extremely important. Okay, so the question is, sorry, maybe I just stop here. Okay, so with my slides, and stop sharing my slides. Yeah. So what my suggestion to again here is that like if we can have students coming into the first year courses, right, and doing basic science and mathematics and a little bit of basic engineering, right, which is common for all, and then after going through that, they choose their area of specialization. That would be the best. Unfortunately, we IITs cannot do this. Okay? Cannot do this because they are admitted into electrical engineering or admitted into mechanical engineering, and there is nothing which we can do in an institutional level for this. We have a whole set of IITs on the national level, people coming together and say agreeing to students being admitted to an IIT and not admitted to a course. Okay? But that's a different ball game. Okay, so let's not worry about that. But there are institutions like, I'm sure Dan Sagar can do this. They can admit students into the institute, okay, into the university, and then give them a 1-year solid foundation. And based on what they do there, okay, and they could choose what engineering they want to do. And I think that would be the best. And we have a lot of opportunity there to teach them, like they're strong, give them a strong foundation. Okay. And any building can be as good as its foundation. Okay, and the same with any other thing. So that foundations we can set, that what we have done instead here is to now in our new regulation is that we said, okay, students can do double major. That's the best we could do. Okay, saying that, okay, somebody has just landed up in mechanical engineering, is actually interested in, more on electric vehicles or electrical engineering, they could also do an electrical engineering major. Okay, that is something which we enable, and of course minor and things like that, to give them a little bit more freedom to choose the topics they want to choose. And if you give them, and I feel they would really be interested in doing getting their foundations right, and there is no question about that. Okay. And I'm so with the industries too. In fact, we had a very interesting conversation with some industry group here in our industry academia interaction, and we asked the industry this question: that what do you think our students should know before they can take up a job in your industry, right? Okay, this question was asked because when we were going through the curriculum review, because our curriculum, this regulations review, we also had industrial participation to discuss this thing. And there were a lot of people who within IIT who think that, like we should give our students more quote unquote engineering and technology so that they become employable, right? Okay. And then when we ask the industries and what their comment was actually almost unanimously, their comment was that when a student comes from an IIT, we expect the student to have a very strong foundation, and rest we will train. Okay, so that was a comment which has come. Okay? So so that is the point. Okay, so we give them a strong foundation, leave it, and the rest industry or whoever wants to train them will do. And if the student wants to take up higher studies, they have the foundation and they can do it. Okay? So that's where I would stop. Okay, and thank you all for listening to me. And if there is any discussion thing, we'll be happy to participate. Yeah. Thank you, Professor Deshmukh.
Thank you very much, Sunil. There have been some out-of-the-box ideas in your talk, and gives new directions to how a curriculum can be redesigned. So there have been brilliant ideas to think through. I think there is a question to you from Dr. Srinivas. Srinivas, can you unmute yourself and ask directly?
Yeah. Thank you, sir. It was very revelating. There's so much of content and, so many ideas that we have to use to redesign our curriculum. I have two simple questions. Sir, do we have to tailor the physics curriculum to suit specific domains, or is it a good idea to design a generic physics curriculum for all the engineering programs?
It's a mixture of both. I would say that's what I'm saying. Okay, I'm saying that there are, first of all, I would always say that physics should be taught by physicists. Okay, and I think you should not make the engineers teach physics. That is not a good idea. So we should teach physics, and then I'm saying that there are some basic things like what I just now mentioned. Like the ability to handle mechanics in a proper way, and handle vector fields and many particles or quantum mechanics, etc. These are basic concepts which they should learn properly. Okay, and that should be common. Okay. When I say common to all things, I probably would suggest separating out computer science, because that is an area. Computer science is an area where they probably don't use any of this. Okay, computer science is more aligned to mathematics. Okay, while computer engineering is different, which is more electrical engineering or computer engineering, that is different, where they definitely need to learn a lot of physics. But computer science as it is may be something different. So I would not suggest that computer science students be forced to take all the physics courses. But otherwise, I think these basic concepts of physics should be a common course, and not go into many applications at that point of time. Just teach the basic concepts, and then you're going to have electives, right? And if there is no time for teaching all the basic concepts, just teach one, but teach one well. And teach one well, and then ask them to take electives. Okay? There is no point in mixing them up and then giving them a flavor. This is my strong suggestion.
Yes, sir. Thank you, sir. Sir, with your permission, just I have one more question. In the guise of hands-on experience, there's a concern that the basic physics behind a problem is being overlooked. Could you please throw some light on this?
No, people can learn through laboratory courses also. Some students are not very comfortable with mathematics. Okay, it's a fact. Okay, and even students who are coming to IIT, for example, I'm saying, okay, they are more happy doing things with their hand and then learn things. Okay, and they do learn well. Okay? So it's not that by doing hands-on learning is not learning concepts well. That is not true. Okay. So they can learn things, they can understand things, concepts pretty well by doing that. So I disagree that like if you just do hands-on, then they will not learn the concepts. But but hands-on also has to be taught, right? Like when concepts has to be taught and insisted on, right? When they give you, after they do a laboratory thing, when you have to have a proper viva or to make sure that the student did understand the concept well. Okay. So that then it will work. So yeah, so we have, for example, enabled what's called open-ended elective courses here, open-ended laboratory elective courses here, in which we say that, okay, now you don't need to, you can, instead of doing a theory course on an elective, you can just do a full open-ended lab project as an elective. Okay, and so that those who learn, who are good with hands can can learn better. Okay, so that should be our focus. Our focus should be to make them learn. Okay, and whatever way they can. So, and students' abilities differ. Some are good at theory and on pen and paper, and some are better with their hands. So I think both are equally good.
Sure, sir. Thank you so much.
Thank you.
One small question.
Thank you. Thank you very much. So we will go over to the next talk. We have a very distinguished atomic physicist, Dr. Bhanu Pratap Das, who is well known across the world for his contributions in many body theory and many applications in atomic physics. And especially now in the wake of the second quantum revolution that is around the corner with quantum technologies, Bhanu is now heading, perhaps unless I need to be corrected, it is perhaps the first private institute dedicated to quantum technologies. So may I request Dr. Yogesh to introduce Dr. Bhanu Pratap Das. Yogesh?
Sir, good morning. Thank you, Professor Deshmukh, sir. I'm really honored to introduce Dr. Bhanu Pratap Das, a distinguished professor and a director, Center for Quantum Engineering, Research and Education. Before taking this position, he served in many internationally reputed institutes, including Colorado State University, University of California, University of Riverside, Indian Institute of Technology, Bombay, Indian Institute of Astrophysics, Bangalore, Tokyo Institute of Technology, and many more. With all this experience, naturally, he received many awards and fellowship. That includes fellow of American Physical Society, a reputed Banvey Smith Fellowship, faculty research grant from Colorado State University, a technical university visiting fellowship from Delft, Holland, IBM Research Support Award, and many more. Apart from this, he is also well known, as our Professor Deshmukh sir told, for his work in the field of quantum physics, particularly many body theory of atoms and molecules, and its applications to fundamental physics and quantum computing. Sir, now we know that quantum computing is known to be the future of computing, and yeah, please, with all your experience, enlighten us. I invite Professor Bhanu Pratap Das, to deliver his talk.
Thank you,
Thank you,
Yogesh. Bhanu?
Yeah, thank you. Thank you very much. I'm honored to speak here today. I'd like to thank Professor Deshmukh and his colleagues at the Anand Sagar University to invite me to give this talk. So let me also share my slides. So can you see my
Yes.
slides?
Yes. Yes.
Okay,
we
okay,
can.
all right. Okay. So just a minute. Right. So the title of my talk is Importance of Teaching Fundamental Physics in Undergraduate Engineering Curriculum. So this was suggested by Professor Deshmukh, and I've added from a quantum perspective, because this is what I've been doing, all my research life. And I'm currently with the Center for Quantum Engineering for Research and Education, as Professor Deshmukh mentioned. And I'm also associated with the Department of Physics at Tokyo Institute of Technology. Actually, I'm still in Tokyo. I hope to return to India next month. All right, so now what I should say is this, that my talk will be a little unconventional. I mean, in the sense that I would like to talk about the subject matter, which is teaching fundamental physics in undergraduate engineering curriculum. But before that, I mean, I would like to sort of make a case for why that should be the case, why that should be so. That is, why is it necessary for engineering students, particularly undergraduate engineering students, to know about quantum technology in general and quantum computing in particular? All right. Well, I mean, as Professor Deshmukh said, we are witnessing a second quantum revolution, and that is mainly because of quantum computers. Now, what's well known is that drug design, discovery of new materials, these are well-known examples of the potential applications of quantum computing. Okay. Other applications include optimization problems. Now, it's a big word, optimization problems. It could mean things like traffic control, traffic routing, which is very important in India. I mean, as you know, I mean, particularly in Bangalore. I mean, when I first went to Bangalore in 1993, I could go from my home to office, which was 3 kilometers in, about 7 to 8 minutes. But that was in 1993. So when I retired around 2015, it took close to half an hour early in the morning. Okay, so that is an important problem. And so you'll be amazed to know that quantum computing is, could provide an answer to address that issue. Then supply chains and many more things. Optimization problems is very important in real life. I mean, when you want to build a house, what's the best way to build a house? That's an optimization problem. And even choosing or selecting a team, a sports team, like the Indian cricket team, that is an optimization problem, because it will depend on which team the Indian team is playing against, and what are the strengths, weaknesses, and what are the strengths and weaknesses of Indian players, and it's already found applications in finance. I believe Infosys has recently got into quantum computing. I didn't know that, just found that out recently. And quantum computing is also, it has potential applications for weather and climate modeling. Now, I should tell you that about 6 or 7 months ago, in this new center in Kolkata, we decided to use our knowledge of quantum computing to address this issue of climate modeling, to explain, to understand climate change. And this was actually suggested to us by the leading agency for weather and climate modeling in Japan. It's known by its acronym JAMSTEC, which stands for Japan Agency for Marine and Earth Sciences and Technology. So, so I was quite happy to know that that part of the Nobel Prize for this year has been in physics has been awarded to for climate modeling. And of course, we all know that an important application of quantum computers is in quantum communication, both space and terrestrial. And that's because this kind of communication is secure. And it's, it's exciting to know that we're making, that we're taking steps slowly but surely towards the establishment of a quantum internet. And well, of course, quantum communication also has national security issues, political issues that I'll not go into in this talk. Okay, but what is becoming clear, I mean, it wasn't clear to me earlier, but it's now that I've started actually getting results from a quantum computer, it's becoming clear that quantum computers could actually revolutionize our world. Okay. Now, just a minute, let's see. All right, so, well, quantum computers are based on quantum mechanics. Okay, so, but let's understand what a computer is and what it does. So this is the classical computing model. Classical by mean a regular computer. So it's, you give input and you finally get outputs, and the inputs are in the form of bits. And so the bits are sort of transistors, and then you have, so the inputs are in the form of bits, and the manipulations are done by gates, which are also made up of transistors, and finally you get the output in the form of bits, you see. So this basic, in a very simple way, this is what a computer does. And when you combine the bits and gates, you have what's called a quantum circuit. And now a quantum computer is conceptually the same thing. That is, you need something like bits, the counterpart of bits. So, but there would be quantum objects. And so there could be atoms, molecules, or even subatomic particles like electrons, or even photons for that matter. Or there could be macroscopic objects like superconducting Josephson junctions and so on. So if we replace bits by quantum bits called qubits, and these gates by their quantum counterparts, you can have a quantum computer. And this idea actually came from a physicist. Many of you have heard of him, Richard Feynman. Okay. And that was about 40 years ago. Now, I would like to say a few things about a quantum computer. The main reason for sort of bringing up a quantum computer and its strengths is to sort of make my case for what topics should be covered in an undergraduate engineering curriculum. So, as I said, a quantum computer is based on quantum mechanics, and now when you think about bits in a regular computer, these are actually states. So the concept of state is very important in a computer. So bits can take the value 0 or 1. So, from a fundamental point of view, a regular computer can be in the state 0 or it can be in the state 1. Now, what about a quantum computer? Now, a quantum computer, as it turns out, yes, it can take, it can be in state 0 and state 1. But as many of you may have, as many of you may know, that the Schrödinger equation, which governs quantum mechanics, it is a linear differential equation. So it's a linear equation. So if state 0 is a solution of the Schrodinger equation in state one is also a solution, then a linear combination is also a solution. So that means A times 0 plus B times 1 is also a state. This is quite unlike the regular computer, which is based on classical physics. So there, we have a second order differential equation. So now this is a great advantage because if you can have 0 and 1 at the same time, a linear combination of 0 and 1 at the same time, then not only do you have access to state 0 and in state 1, you also have access to 0 plus 1 and linear combinations. So you have many more states to do your information processing. So, so if you take 1 bit versus 1 qubit, a qubit will give you many more states for doing quantum information processing. You can process more information with 1 qubit than you can with 1 bit. And if you have 2 bits, you have 2 states. But if you have 2 qubits, you have 4 states. It grows exponentially 2 to the power n. So if you have n, you have 2 to the power n states, and actually linear combinations of those. So, so therefore, you can, in a given time, you can do more calculations using a quantum computer than its classical counterpart. But of course, I have to say that not all problems are amenable for solution in quantum computers. Many are, some are not. Okay. Now, there's another thing which I should say here. There's a special kind of superposition called entanglement. So, okay, before that, I should have said that this linear combination of 0 and 1 is called a qubit. So a qubit means that a qubit can be in 2 states, 0 or 1, and also in a linear combination state. Now, entanglement is a relationship between 2 qubits. That means the two qubits are correlated. That is, if you have 2 qubits, 0, 1 together, and yes, so you can have a state which is A times 0, 1 plus B times 1, 0. So 0 becomes 1 and 1 becomes 0. So that is called an entangled state. And that, again, you don't find in classical physics, you see. So these entangled states are very, very special, okay? And they are linear combinations, they're linear combination states, but a special kind of linear combination states. So, so this linear superposition and entanglement is what makes a quantum computer very special. And this has implications not only for a quantum computer, but for quantum communication, as I will mention later. Now, here I'll give you an example that if you solve the states of an atom or a molecule using quantum mechanics, you will find, well, you can show that the states are entangled. Now, this is not widely known, even for people who do atomic and molecular physics, that the states that they deal with are entangled. Entanglement is not a feature of classical physics. Classical computers can handle entanglement, but quantum computers can handle them much better because you can entangle qubits in a particular way. Now, so therefore, if you're trying to solve an atomic or a molecular problem using a quantum computer, it's potentially much faster than it would be to solve on a classical computer. Now, this, of course, has important implications for drug design and discovery of new materials, because when you're talking about a drug, you're basically talking about molecules. And again, when you're talking about new materials, you're talking about it at the level of atoms and molecules. So when you think of drug design and new materials at the level of atoms and molecules, then it would be much faster to do them, to do the simulations on a quantum computer than a classical computer. So this actually holds promise in this field. Now, The next question is, what are qubits? Now, qubits are not transistors like regular bits, but they're made up of quantum objects. They can be solid state like Josephson junction. You can also have silicon qubits, and they could be atomic, like they could be neutral atoms, or they could be ions, or they could be optical, photons. Photons are very good qubits, and they're not only can you make a quantum computer with photons as your qubits, but you can actually entangle photons. And that is the basis of quantum communication. So if you can't entangle photons, then you can't use it, then you can't have quantum communication, at least at a practical level. Okay, so a quantum computer is qubits plus quantum gates. Now to build that, you need physicists and engineers. So I'll not go into the details. I'll just say that knowledge of physics, because knowledge by physics, I mean quantum mechanics, and engineering skills are needed to build a quantum computer. So, and quantum computers are being built in big tech companies like IBM, Google, and so on. And in startup companies like IonQ, Rigetti, etc. Universities. Actually, most of the quantum computers that are built in China are in universities, and China is leading the world in quantum computing. University of Tokyo, and I have collaborative projects with the University of Tokyo, also has quantum computers, not very large, not as big as the ones in China or in some of the big tech companies, but it's about 16 qubits, but you can do a lot with it. Okay, and in research institutes, many research institutes like national laboratories in the US, are making quantum computers. And in the new research institute in Kolkata, where I am, that's what we plan to do in the future. Okay. Now, an example of where physicists and engineers work together to build quantum computers is MIT. I mean, there are many more. I mean, I can think of, for example, Technological University Delft in Netherlands, but let me talk about MIT. Now, in MIT, the physicists and engineers, I mean, are part of the Center for Quantum Engineering. Now, well, here I have a slight difference with what Professor Sunilkumar said, that that physicists and engineers should teach courses together. That's fine, and that physics courses should be taught by physicists and not engineers. That's also fine. But in MIT, you'll find there's hardly any distinction. I mean, at least in many cases, and I'll illustrate that through through quantum computing. Now, people in MIT, the professors at MIT who are involved in building quantum computers are mostly from the electrical engineering department, but they're also physicists. So there are engineers, you'll find electrical engineers who know engineering and physics equally well. Okay. And I can find many examples. I'll just limit myself to MIT. Now, the head of the Center for Quantum Engineering at MIT is a person by the name of William Oliver. All his degrees are in electrical engineering, but if you look at his master's and PhD thesis, it's basically quantum mechanics or applied quantum mechanics. So, and he teaches full-fledged courses in quantum mechanics at MIT, quantum mechanics, applied quantum mechanics, and so on. Now, another person whose names many of you may have heard of, Isaac Chuang. He's the author of the well-known book on quantum computation, Nielsen and Chuang. Chuang, if you've read his book, you'll probably feel that he's an expert on quantum mechanics. He certainly is. But his training is in electrical engineering, from his undergraduate days. He's been interested in quantum mechanics, and He is primarily a professor of electrical engineering at MIT and also has a joint appointment with physics. Rather, people like Rajiv Ram, who is into photonic quantum computing, and perhaps many of you have heard of Seth Lloyd, who is a theorist. I mean, who's very famous for quantum algorithms in a variety of areas. And probably, if you know his work, but you don't know his affiliation at MIT, you'll be surprised to know that he's a professor of mechanical engineering. Now, his training has been in physics, but the mechanical engineering at MIT felt that they should have someone like him, to familiarize or to at least expose the important ideas of physics to engineers. So he, is equally comfortable with both. So so scientists and engineers and people from other areas like finance, they've started using quantum computers, and this trend will grow in the future, as you see, will grow in the future. So clearly, engineers who will be building and using quantum computers will benefit from a good knowledge of quantum mechanics. If engineers are building quantum computers, they're using quantum computers, then it certainly will help if they have a good knowledge of quantum mechanics, because then they can use it more efficiently, more effectively. So, yeah, now with this rather long introduction, let me just talk about some of the physics courses that are offered to students at Dayanand Sagar University. And the information that I got is from Professor Deshmukh. Okay. There's a course on engineering physics. I believe it is taught to first-year students. That's fine. I mean, I personally would have preferred if that had been taught in second year. And I also think it should be a 2-semester course rather than a 1-semester course. And all the topics, I think, that are in that course are important and useful. When engineers, students with an engineering background want to work on sort of solid state kind of problems, semiconductor related problems. But I feel that ideas on superconductivity, particularly Josephson's junction, can be introduced at a simple level. I didn't find that in the syllabus of that course. That is because currently, that could change in the future. Currently, the best platform for quantum computers seem to be Josephson junctions, that is qubits, which are made from the Josephson junction, where the superconducting current passes through the junction. So now that can be a good qubit because the current can flow in the clockwise direction or the anti-clockwise direction. So there are 2 possible states there, corresponding to the direction of the flow of current. So therefore you can have 2 states, and therefore that can be a qubit. All right. So I also feel that in that course, there could be a simple introduction to the photon and some of its properties. Now, of course, you can introduce the photon in a very simple way by saying that it's a quanta of light, and that light has both wave-like and particle-like properties. So if you want to talk about the particle-like properties, then you have to use a photon. So you can start with that idea, and then talk about the different states of photons, the different polarization states in a simple way. Now, of course, I mean, you can also, treat photons from the point of view of quantum field theory, as the gauge bosons for electromagnetism. I mean, that's not necessary. That kind of treatment is not necessary for learning about a quantum computer. So, the teacher could decide at what level they want to introduce the idea of a photon. Now, why do I say that? I say that because photons can be qubits for a quantum computer. And photonic quantum computers are doing quite well. So calculations have been carried out using a photonic quantum computation. Not only that, I think in December 2020, quantum supremacy was achieved using a photonic supercomputer, sorry, a photonic quantum computer in China. So quantum supremacy means when a quantum computer outperforms a classical computer. And there are only 3 such cases so far, 2 in China and 1 in US, Google. So the second case involved using a photonic quantum computer at the University of Science and Technology in China in collaboration with many other universities. And well, the other 2 cases were both superconducting quantum computers, but a photonic quantum computer could calculate a problem. I mean, could calculate a problem involving photons in about 2 seconds, and that took billions of years on that would have taken billions of years on a classical computer. So it outperformed a classical computer by 14 orders of magnitude. That is, it was 10 to the power 14 faster. Now, these are some selected problems, and quantum supremacy is not very common yet. But what I'm trying to say is that photons are really important in quantum technology, whether it is for quantum computers, as I just mentioned, and you just can't do without photons for quantum communication. It turns out that photons can be entangled, and entangled photons can be the carrier of information. Okay, so if you want to use it for communication, and here China has completely actually it's China who set the trend, and other countries are trying to catch up. Even the US is far, far behind China in quantum communication. People in ISRO have talked to me, I'm no expert in this, about quantum communication using photons, and I have given them what little material I have with me, and they certainly are interested, and I mean they have probably carried out some simple experiments. People at Raman Research Institute are also interested in this area. So I think this, the properties of photons should certainly be part of this introductory physics course. Now, there is a specialized course, elective course, I think for 4th year students, called Entanglement and Introduction to Quantum Computing. So that course, I think, is for 4th year students. I think it's an excellent course from the syllabus that I saw. I mean, it seems like an excellent course. And clearly, linear algebra should be a prerequisite for this course. And students who will be taking this course should have linear algebra as a prerequisite, I think. Yes, this course has both quantum computing and quantum communication. And that's a very good thing, I feel. So I think even teleportation was mentioned as a topic in that in the syllabus. I think in addition, the basic ideas underlying a quantum internet could also be introduced. Now, quantum internet has been demonstrated at a simple level, both in China and the US, and actually in Europe, in Delft. The Delft University of Technology have also demonstrated this as a proof of concept. And here, again, you need photons, an entanglement between photons. And you need different nodes, just as computers serve as nodes for the regular internet, quantum computers can serve as nodes for a quantum internet. Okay. Right. Another thing that I think I should really emphasize is this idea of quantum annealing. quantum annealing is a second approach to quantum computing. You know, what I've talked about so far are quantum computers for which you need both qubits and quantum gates. Okay, that's called universal quantum computing. Now that it's universal because it can do any problem in principle, and there's a lot of flexibility and control because you have gates, so you can use the gates to control the calculations. You can manipulate in different ways, but the problem is that gates lead to a lot of errors, and the gate fidelity is often an issue. So quantum annealing is a second approach to quantum computing, which avoids using quantum gates. It only uses quantum qubits. Interestingly, this idea was proposed by a colleague of mine at Tokyo Institute of Technology. And sadly, I didn't spend too much time trying to learn from him. That's because it's only in the past 1 year I've realized how important quantum annealing is. So I could have really talked to him in person, but now I have to correspond because of the pandemics and so on. I have to talk to him on Skype or Zoom and understand things better. Quantum annealing is excellent for optimization problems, okay? And as you know, in real life, there are many, many optimization problems like traffic control, supply chains, and as I was telling you, selecting a cricket team or any sports team, and so on. So actually, it just came to my mind that after you get all these inputs, you can use a quantum annealing machine to decide what physics courses should be offered to engineering students, undergraduate engineering students. What you do is you give all the inputs, okay, and then you state your objective, and with all the inputs and with the objectives that you've mentioned, a quantum annealer will choose an optimal course for you. Okay, I think you can try. And quantum annealing, the first ever quantum computer was a quantum annealing computer. That was by a company called D-Wave in Vancouver, Canada. And it's much easier to build than a regular computer, than a regular gate-based computer. Now, the regular gate-based universal computer, the maximum number of qubits that one has now is 66 qubits in China and 65 qubits by IBM. The quantum annealer now has 5,000 qubits. Okay. And that's because it's much easier to make. You don't have gates, so it's easier to make that. Now, the final thing I'd like to say is that the elective that has been introduced is very desirable. I think it's a very good course. But I think it should be complemented by a course in quantum software. And this will give hands-on experiences to students with packages like, Qiskit. Qiskit is the IBM software for quantum computers. Okay, now, let me say a few things very quickly. Why do I say this? Why do I say that a course in quantum software is necessary? Now, for that, you don't need to have a quantum computer. Okay, I'll explain why. Because, see, there are in this whole field of quantum computing, there are three broad areas: theory, software, and hardware. So by theory, I mean that you decide the problem that you want to solve. Could be finding the properties of an atom. Then you need a quantum theory. If the problem is to model the climate, then you need a classical theory based on your understanding of atmospheric science. Okay, so then once you have a theory, once you have a conceptual understanding, then you write an algorithm. An algorithm basically means it's a method of solving a problem, and the method it would be a quantum algorithm because it's meant for a quantum computer. It doesn't matter whether the problem is a quantum problem or a classical problem. What you need is a quantum algorithm, an algorithm that will run on a quantum computer. Okay, now that's the first step. The second step is to write a code or write codes that can be run on a quantum computer. You can also write codes that will be run. You can have a quantum algorithm and you can write software for a regular classical computer, or you can write software that is meant for a quantum computer. So theory, software, and the final step is hardware. That means a real quantum computer or a classical computer. So in the beginning, I think it's a good idea to take a problem, write a quantum algorithm for it, okay, then do the software. Do the software for a classical computer, run it on a classical computer, but it's a quantum algorithm, okay? So, and get the results. And then if you have access to a quantum computer, then do the same for a quantum computer and compare the results. Then you can use the results of a classical computer to benchmark your results for a quantum computer. And because the quantum computers we have now have a limited number of qubits, they can't handle big problems, and there are errors and so on. So you can know how good the present quantum computers are, I mean, with a few qubits compared to the results of a classical computer, you see. So if we have a course for engineering students, well, the problem could be any problem, I mean, it could be a quantum problem or it could be a classical problem. And I mean, I always think about climate modeling because that's what I'm sort of trying to work on these days. So, or, whatever else you think would be useful for you, write a quantum algorithm for that. Then write a code for that particular algorithm. So write the code for a classical computer that will be available to you. You can certainly use a classical computer. If not, you can try to access the computer that CDAC has. I mean, they have a scheme whereby anyone in the country can use their machine. I mean, it doesn't have to be their biggest machine. It could be a smaller machine, and then run it, you see. So that will give you experience with quantum algorithms and some amount of experience with software. And the results will be useful for benchmarking when at some point in the future, if you can access a quantum computer and get the results. So you can compare the two results. So I think such a course will be useful even without a quantum computer. So that's what I would recommend. Now, how do you do all this? Perhaps you need a quantum annealer, I mean, to optimize such a course, you see. So with these few remarks, let me stop, and I'll be happy to answer questions. Thank you.
Thank you. Thank you very much, Professor Das. This has been a very insightful talk. I'm sure there will be a number of questions, but I think this is a new field for many in the audience, so they may take some time to frame their questions. And as and when I receive them, I will send those queries to you by email or something. But there have been excellent suggestions about how to improvise the curriculum. What are the things to be added? And I think your suggestions to add an aspect of quantum internet, quantum annealing, these are very constructive and viable suggestions which can be incorporated in a fairly straightforward manner in what we have in the effort that we have initiated at the Dayanand Sagar University. There are, of course, many other things that you said which will be extremely useful to us. So thank you very much. And
Sir, one question, sir.
yes,
Sir,
yes,
I can
Vijay,
submit one
please,
question.
please.
Sir, I think we are in the next semester. We are planning to introduce one elective on fundamentals of quantum computing, especially for the computer science engineering students. I request to the Bhanu Prakash sir, how it is justifying this quantum computing for, especially for the computer science and computer technology students.
Yeah. Well, that's a very good question. You know, I mean, you see, I mean, computer science students are exposed to the general idea of the theory of quantum computation. Okay. Now, so computer science students can approach this from a purely theoretical point of view regarding what are the limits of a quantum computer. They could do that. Or if the computer scientists are more numerically minded, then they could come up with certain problems. And then, as I said, follow the steps, like come up with quantum algorithms. You see, I mean, some of the best algorithms that exist now have been from quantum scientists, sorry, for computer scientists. Like there's an algorithm called a Grover algorithm. Grover is from India. He's in the US. I mean, it's basically it's for searching data. It's a data search algorithm that was proposed by Love Grover, who is a computer scientist at Bell Labs. And another very good algorithm is by Vazirani, Umesh Vazirani at the University of California, Berkeley. So as a matter of fact, I mean, what I would recommend is for students to listen to Vazirani's lectures on quantum computing, which he teaches in the computer science department at the University of California, Berkeley. So if you go to YouTube and give Vazirani, Vazirani, Vazirani lectures on quantum computing, you'll find all the lectures. He's an excellent lecturer, besides being an excellent computer scientist. And you'll get an idea about what is needed. I mean, what kind of background do you need in quantum mechanics for computer scientists to use quantum computers? So to the best of my knowledge, the main contribution that have been made by computer scientists to quantum computing has been the area of quantum algorithm, particularly by Grover and Vazirani.
Okay, sir. Thank you, sir. Thank you a lot for your kind information. We can follow some talks and some other books also we can search.
Thank you very much, Dr. Das, once again. We are now, we now have the next talk, and we are all very proud of the contributions made by ISRO to the development of science and technology in India. And we are very proud and privileged to have Satish Dhawan Professor P. Sunilkumar with us, who has led many of these projects with ISRO. And I should mention that Professor Sunilkumar is one of the persons who has also inspired a large number of young minds. So it's a great privilege for us to have him with us. May I request Dr. Vaishali to please introduce Dr. Sunilkumar. Vaishali? Vaishali, you had to unmute yourself.
Yes, am I audible?
Yes, now we can hear you.
Good morning to all of you. Dr. P. Sunilkumar pursued his PhD in physics at the University of New Hampshire, US, in the area of gamma rays astronomy. As a core member of the science team of the Compton Gamma Ray Observatory, he pursued his research in the area of extragalactic diffuse gamma ray emission at NASA Goddard Space Flight Center for a decade. In 1999, he returned to India and headed the Space Astronomy Group at the ISRO Satellite Center. In 2013, he was deputed to be the director of Indian Institute of Astrophysics, Bangalore, for a period of 5 years. In July 2018, he returned to ISRO to head the Space Science Program Office at ISRO headquarters. He is presently the Satish Dhawan Professor at ISRO and advisor to Space Science Program Office at ISRO. Dr. Sunilkumar's research area includes cosmic rays, gamma rays, solar system X-ray studies, and ultraviolet astronomy. He has contributed to the design and development of many space payloads, including Chandrayaan-1 and 2 as PI and co-PI. His current interest is on the development of multilayer mirrors for X-ray polarimetric studies. Before I hand over to Dr. P. Sunilkumar for giving his talk, I would like to add a small thing that when he was the group director at Space Astronomy Group, he had given me permission to be there, visit the center for almost 2 years. At that time, I was a PhD student at IISc, and he has been kind enough to give me permission to go there and perform a major portion of my experiments there. I'm really thankful for that one, and today it is my privilege to invite you for a DSU lecture. Sir, over to you. So many times we have interacted, couple of times we have interacted, and every time he would give me ideas for experiments that will be from some other perspective. So with that, I really cherish those interactions with sir. Over to you, sir.
Thank you, Vaishali. Thank you, Professor Deshmukh. Thank you, the management at Dayanand Sagar. It's an honor to be part of this discussion. These are indeed ideas that or concerns that we ourselves have in many forums. We discuss how to really improve the quality of education overall, and in particular the interface between physics and engineering, which is particularly of great interest to me. My experience as a teacher is rather limited compared to all of the panelists. He's been limited to limited teaching, mostly at the PhD level, and then otherwise, of course, at basic teaching that I have done at St. Joseph's and other places. But that shall not prevent me from expressing some views. So the question in front of us is in terms of, I look at it is in terms of what can we address with regard to unique gains that will come from a deeper exposure of physics to engineering students. And to some extent, I would also want to look at in terms of the engineering exposure to our physics students. Because, at ISRO, we have a blend of both, and I'm strongly convinced that it's this interface that really helps us go forward in many innovative areas. So we are all aware of this enormous contribution made by physics towards the growth of many engineering fields. We just now had a long, a very detailed and convincing discussion from Professor Bhanu Prakash on how quantum mechanics and the emerging fields of both computing, communication, etc., have been addressed. Physics, of course, provides this foundational physical laws that governs the universe, and we look at it in the context of technology from the engineering side. So this deep theoretical understanding of systems, well-supported mathematical experiments is absolutely beneficial for many areas of science. So what is often seen as very specialized esoteric areas of theoretical physics have now found critical applications in numerous areas of engineering. Real-life projects that we often have to face as we pursue a career are like autonomous navigation, a hot topic, design, development, space systems, etc., demand a lot of interdisciplinary inputs and expertise. And this is the key to many new emerging areas. We have numerous mega projects in the country, often in the area of sciences, initiated with support of multiple ministries, atomic energy, Department of Science and Technology, Department of Space, and so on. And this includes our roles in the large 30-meter telescope program, the third gravitational wave detector, the LIGO lab in India, and also the big new radio observatory, the Square Kilometer Array. These are really major programs where we see a tremendous interface between physics that we learn in the school, that we learn during a research phase, and the engineering that is necessary to pursue these long-term goals. Our students today are really looking forward to having a prominent role in this as they look at their future careers. So beyond the traditional training now being imparted, what are additional skills that are critical to make a real mark in these areas? In my view, understanding the main underlying assumptions on which some of these designs or analysis are built is key towards creating new breakthroughs in the field. We can't take any equation to be absolute in terms of when it comes to application. They're all built on assumptions. Knowing these assumptions and knowing the limits of these assumptions are critical as we look forward to improving upon these things. While a large section of these global mega projects come with predefined designs, many a time we are often only doing 10% or 20% of this total project, there are still many areas where India can play a leading role with innovative designs. These design roles also significantly address risk reduction, cost reduction, and enhanced reliability of systems. And these are real practical issues that have to be dealt with when you're looking at global large-scale problems. And physicists often shy away from this. There's a lot for them to learn from the engineering teams. Today, we have regular physics and engineering programs which follow traditional syllabus. Often it's a slow response to emerging developments and new research. Some institutions have been more responsive in responding to these emerging developments and have provided new avenues for students to get exposed to areas. At the Dayanand Sagar University, I see from the online material, I see that the computer science and engineering branch offers multiple contemporary areas of specialization. New electives are being proposed in physics in the areas of quantum revolution and relativity and chaos that Professor Deshmukh shared with us. I think these are very well designed programs. Engineering physics, which has been there, and if it's just a single course, as Professor Sunilkumar said, may not serve us the full purpose, but engineering physics in a more extended form could even be in the form of a complete program. Today, the Indian Institute of Space Science and Technology has an engineering physics program, as well as many IITs. These are offered at many institutions. They tread the middle path between physics and engineering. It provides a unique blend of subjects that enable engineering-oriented students with the foundations of physical laws that govern the universe towards technology designs. It can also provide exposure to a wider canvas for future focus areas. This could be in areas of microscopy, quantum optics, nanotechnology, microfabrication, etc. So students pursuing in engineering physics often get a fairly good, what I call a minimum exposure to the subject, which allows them to say, is this something of interest to me? Shall I pursue that as part of my future program? One of the areas in these areas of education, I feel that it certainly requires much attention is strengthening the students' understanding of subjects beyond the classroom interactions. Classroom interactions, of course, limited, as Professor Sunilkumar said, many elements of requirements have to be balanced. Typically, the student-teacher interaction in our college and many parts of the country are passive, one-way interactions. We need to strengthen this. Independently allow them to think, ability to confidently make rational conclusions and decisions. I mean, decision-making appears to be set aside for a much later phase in their career. And I think this is something that is very, very critical. With whatever information that we have, what is the best choice of options that we need to take? Voice their views logically in open forums. Their communication skills are not adequate enough often for industry. Associating groups of students to a faculty advisor who could actually trigger this would be very helpful in assessing specific areas that require strengthening and maybe critical to the overall success of any program that we are looking at in the future. In particular, the overall goal of this education, that is to retain interest in the subject. Innovation can only come if there's interest in the subject. And I think that's very important to nurture at the undergraduate level. The new education policy suggests a 4-year UG program, even for science streams. The 4th year, in my view, could be used to strengthen the theoretical material taught in the first 3 years to give valuable experience to students, and particularly in the areas of experimentation. Hands-on labs, when well thought out programs, are critical to understanding the underlying principle. It does allow students to really see what is often being taught in class in a more, from a different perspective, and experience the joy of research. I think this is very critical. Time is short, so the curriculum need not have to cover many topics. Our goal need not be to do every experiment that's necessary, but even a single end-to-end program that goes from design to partial realization can be very effective. I recall a discussion for the PhD students at the Joint Astronomy Program at IISc that 5, at one time 7 research institutes used to participate along with IISc in doing the PhD program in astronomy and astrophysics. We have a laboratory program there, and the laboratory program has not been very successful in my view, and partly because we've been trying to teach a lot of things in one semester. In my view, even a single experiment taught from basic concept of design to how we go on doing realizations, how some testing can be a very effective way to actually understand, to give students a pleasure of actually and the challenge of doing experimentation. A second area, which is really underlying undergraduate research projects. It can be an eye-opener for them. Again, the question, of course, is how do you blend that into the already busy schedule that is currently there in the syllabus? But certainly it allows emerging areas of science and technology. It allows group research activities. These build essential skills necessary as our students explore career options. I recall the pleasure of actually seeing IIT Madras students when they're working on the small satellite that when I first interacted with Professor Deshmukh. The pleasure was not in exactly knowing what they're doing, but the way they were solving problems, the way they were discussing. That is very, very critical. I think group research activities is very, very critical. And they should actually participate in discussions and presenting their well thought out ideas in various forums. And undergraduate education, if it also provides an exposure on how to write research proposals or a research paper, the basics of it is actually very important. How does a peer review process actually look at your product? As soon as they complete the program, either in higher education or for their industry or employment opportunities, these are going to be tested. So the ability to write a meaningful research program or a research paper is very critical. And I know some of the departments and universities do provide that. IIST has a program on communication skills for that under the engineering sciences program. NEP also talks about vocational training and academic education and the need to provide multiple exit strategies for students enrolled in traditional degree programs. Everyone who enrolls in a program need not have to come out with that particular degree. Midway through, there may be different thinking, there may be different skill sets that can be further encouraged as opposed to forcing all of them to really become either engineers or scientists. Engineering and physics provides ample opportunity for skill training, and niche electives emphasizing these application areas such as biomedical, data sciences, expertise with precision measurements, calibration, etc. be offered at different institutions and encourage alternate skill sets and widen career prospects. We need equal expertise with advanced tools and measurements, as with other skilled activities are often demanded when we do that, when we are using, hiring faculties and others who use these measurements to model and provide theoretical foundations. So skills are as important as core fundamental concept development. So there's a need to transition from terming vocational trained students as losers, I would say, to specialists, to advance them overall skill development in the country, to build an environment of mutual respect for different professions. In sciences in particular, there's a prevalent hierarchy of theory at the top and experimental sciences at the bottom, which widely is prevalent and prevents growth in many of our collaborative programs. And this is, of course, often seen when we're looking at mega projects where we have difficulties in actually attracting some of the best minds into experimental sciences. Finally, let me speak a few words on the importance of learning together, to work together in collaborative programs. A common thread that we see in many R&D programs, as I just mentioned, is the absence of connection within our academic research community on the gains from collaborative programs. There is, over the years, a greater emphasis for individual growth and research programs, but in the modern world, collaborative programs are certainly very critical. It has been in the past as well, but certainly we need to really look at it in the future. ISRO's success has been its ability to bring together varied groups of different caliber, of different kinds of expertise into a collaborative, goal-oriented project with clear deliverables. as outlined by Professor Sadiq Thavan many years ago. So it's very important to inculcate this at an early age, an appreciation for collaborative research. Even if you do not agree with each other on personal matters, I can still collaborate with people. This is something we need to know. We need to show that we gain, not lose, with collaborative research. It's critical to maximize the use of existing facilities. Everybody doesn't need a computing lab in their background, in their own lab. We can share facilities. There are many examples in India and elsewhere that show successful collaborations. So if we could gain or evolve some steps that actually will allow our young minds to appreciate this, I think we would have made a major step in that direction. How could we do this? A suggestion from my side would be to provide students with exposure to this interdisciplinary research by involving them in student-driven design exercises of a complex experiment. I say design experiments because they cannot really build it in the time scale that they have, but even a design process, going through the process of design would be very, very valuable, where they interact with each other, they really learn to get inputs from others, appreciate the value that someone else brings in with an expertise from a different angle. The choice of these could, of course, be different to faculty interest, expertise, and available facilities at every institution. Nationally, successful collaborations should get highlighted along with individual collaboration when awards or recognitions are considered. While we may have we may evolve a good plan on paper, implementing that will be key. And I do realize today's discussion is not on implementation, but I'd like to stress the need to adopting practical steps towards a successful implementation of NEP takes into account the use of the critical player in this, and that is the teacher. So our goal overall is to really ensure that we create and retain interest in the subject for our students, maybe more than the volume of knowledge, and only then innovation will emerge. So as we look towards augmenting our education system for future, we must stay focused on original thinking, identifying and building expertise in niche areas which exploit new developments in science and technology, and this would be very, very rewarding for our program. So I'll stop with that and come back if there is any points for discussion. Thank you.
Thank you very much, Dr. Srikumar. You brought out, of course, from your very rich experience of leading big projects, the importance of teamwork and collaborations. I think it is very important to inculcate this culture right at the level of undergraduate education. So thank you very much for your guidance. There may be some questions. Maybe Dr. Srinivas wants to add anything.
Yes.
Srinivas?
Yeah, thank you, Professor PCD, sir. Sir, we have an aerospace department in our university. We have a BTech program in aerospace, which is started about 3 years ago. So do you have any advice on what kind of physics could be suitable for the aerospace engineering?
I mean, I have not. You must be teaching them some. They must be getting exposed to some physics already. I mean, with regard to when you look at the role of physics in these programs, it is to really build the fundamentals and to be able to think about how to really construct models and how we can actually use the basic fundamentals to actually build the application that one is working on. So it's clearly an important area with regard to looking at the, if somebody is actually involved in trying to look at the areas of designing of aircrafts, interaction between atmosphere, the nature of the environment in which the atmosphere is, the atmospheric parameters change, etc., are all being taught right now. But the real objective of the physics, I think, should be to really say how fundamental laws actually be used to really derive these application areas, and what those limitations will be of these fundamental laws. For example, when you say when friction is actually taught in class, we know what friction is, but when friction has to be challenged in a technology environment, it is an entirely different issue. What are the limitations of those theoretical areas? We need to know. Where does turbulence come in? What are the limits of turbulence as we understand it today? These are the kind of issues that we must try to emphasize. So within the time scale that you have to really keep them in the class, given other pressures of syllabus, an appropriate choice of subjects have to be derived. I do not particularly, since I don't teach these courses in myself, I personally give that to you now, but I do know the program at University of Space Science and Technology in Trivandrum where they have an engineering physics as well as they also have aerospace program. There are certain courses that are actually put into these. I'm sure there are similar things at other IITs as well. It might be worthwhile to look into that and then see how best to adopt that for your needs.
Sure, sir. Thank you so much.
Maybe Dr. Sunilkumar wants to add something on this, because he also alluded to the importance of teaching vector calculus and maybe a strong course on fluid mechanics, which is based on the foundations, would be of importance. Sunil, could you elaborate on that?
So aerospace is again a very interdisciplinary area today, right? Because there is mechanics, of course. There is fluid mechanics, and there is other solid mechanics. Everything comes in there, as I mentioned. But there's also control there. There's a lot of control subjects there, and so there is a whole lot of areas of physics. So I think, but of course, you can say that you must, an aerospace engineer should definitely know both solid and fluid mechanics, for sure, right? And some amount of complexity, but I know that is I guess maybe not in the UG level, but it's, yeah, right. That's what I could immediately propose.
Yeah. Srinivas, any further questions or comments?
Yeah, I think it's fine. I got some idea on what I had in
I
doubts.
have a small question.
Yeah, please.
Sir, yes. Srikumar sir, is there any provision of the students, UG students, to collaborate with ISRO and do some design, project kind of thing? Is it there, particularly for the UG students, where they can go as a group and they can interact and get some mentoring?
I wish there was. But
Okay.
I know various factors have stopped us from actually being able to do this. I mean, we did actually, I think about 15 years ago, I had actually managed to get a team of undergraduate students from St. Joseph College, which actually had students also from other colleges. It was a Saturday course we used to offer. So I had actually enabled them to come on weekends to really do experiments, etc. But these were days when I think the entry into resources centers was much simpler and easier. Today is very, very tough to do. That's one part of it. The second part, of course, is the fact that undergraduate research is not, since it's not a point of focus, it is not always coming through as a request. Now, it's nice that you have actually put in this request, but we don't get too much of such requests from many places. At the master's and the PhD level, there is a lot more such requests, and that happens on a case-by-case basis at different centers, but there is no formal organized process. There may be some emerging things coming up in the future, given the new space policy under which ISRO will be looking at R&D in much greater detail. And I'm hoping that is a time when academic institutions and ISRO will have greater partnership with regard to student involvement, even at undergraduate level.
Okay, thank you.
Well, I think it has been a great privilege for the Department of Physics to have such distinguished, eminent scholars, scientists, technologists who have contributed so much to the frontiers of science and technology. And it's impossible to thank Dr. Sheikh Mande, Dr. Sunilkumar, Dr. Sri Kumar, Dr. Bhanu Das, who have given their very valuable time. But the Department of Physics would like to express its gratitude. And on behalf of the Department of Physics, the head of the Department of Physics, Dr. Vijay Kumar, will do it for us. Vijay?
Yes, sir. Once again, good afternoon to everyone. So it is an honor to have been asked to offer a vote of thanks on the occasion of the Physics Colloquium on significance of physics in engineering curriculum under new education policy 2020. Sir, on behalf of DSU School of Engineering, I will thank the Honorable and respected Chief Guest and Resource Persons, Dr. Chandrasekhar Mande, Director CSR, and Dr. P B Sunilkumar, Director IIT Palkot, and Dr. P. Sri Kumar, Satish Dhawan Professor ISRO, and Dr. Bhanu Das, Director TCG Sequare. On behalf of DSU and Department of Physics, I am very hearty gratitude to all the eminent speakers for sharing their ideas and their graceful words scientifically with us in today's Physics Colloquium. It has been our tribute to specially thank our Pro-Chancellor, Dr. Prem Chandrasekhar, for his motivation and support. I will thank all the members and the audience of the today's event. I'm thankful to all the faculty participants and students for participating in the Physics Colloquium. So we have been fortunate to have a renowned identity from academics, industry, and other areas. I'm very thankful to the entire participants of this webinar. I'm sure that our department will continue to get significant provision from diverse groups in the future also. Finally, I will thank all the respected resource persons, Pro Vice Chancellor, and Vice Chancellor Dr. K.N.B. Murthy and Secretary Galiswamy DSI and Pro VC Dr. Janardhan Sir and Registrar C. Putumadappa and Dean Srinivas School of Engineering and my physics faculty colleagues and the technical staff in charge. So once again, finally, I will submit our thanks and gratitude to expert resource persons. Thanking you all. Jai Hind.
Thank you all very much.
Thank you, sir.
So,
Thank you a lot.
goodbye for now. We
all the
will
respects.
continue. Yes,
Thank
we
you.
will
Thank
continue
you.
to approach our distinguished scholars and eminent speakers for their guidance. So thank you all very much and goodbye for now.
Thank you.
Thank you, sir. Thank you all. Thank
All right.
you. Namaskar.
Bye.
Namaskar.